Cool. So this graph I drew yesterday, we talked about like as you guys were leaving. I'm going to give you guys like 30 seconds or so to chat with your neighbors and tell me what's going on in this graph. Why do we talk about it? Why do we draw it? But here's how I think is the easiest way to go through here. I've added these intervals. From A to B, that amount of time, what's happening? Are you sure?
It's getting warmer.
What's getting warmer?
The thing.
What's the thing?
The solid.
What's the solid?
The matter.
So I'm going to keep going until we get the right one. We're talking about what very specific type of matter? Oh, water, right. That's what we're talking about. Okay, so you guys, your answers weren't wrong, just so you know. Yeah, like matter, atoms, they're all involved. From A to B, though, I'll tell you, we are not melting. And this is a weird idea because you don't often think about it. I could have a really cold freezer and my ice could be at 50 degrees below zero, negative 50. I could heat my ice up to negative 10 without it ever melting because it hasn't gotten warm enough to melt yet. So from A to B, all we see is ice temperature increasing. And again, it's such a weird idea because when we think about ice, we think about it being solid and just being solid and then melting, but it can be different temperatures of ice. Okay, from B to C, we are adding energy into this thing still, and it stays right at 0 degrees. Now, what's cool about that is the outside of the ice, it's still frozen. It's 0 degrees. The water that just melted off of it is 0 degrees. Like they're both the same. So we have a liquid and a solid at that point in time. As I keep adding energy, the temperature never increases until all of the ice becomes liquid. So B to C, this little stretch right here is where we really see the ice melts. Okay, we at point C then are in just, if it's a jar or whatever we're dealing with, we just have a jar of liquid water at this point that's at 0 degrees Celsius. Wonderful to drink, super duper cold. All right, from C to D then, what is going on? Too many answers at once, sorry about that. What do you think, Adam? From C to D, we just melted all the ice and turned on the liquid. So careful, we're right here. Give it a second. So we will, because I'm not just going to let you skid off of this. Can you tell me any rough temperature in here? Like at this point in time, what is the temperature roughly? It would not be steam yet. Like it wouldn't be gas yet. It would just be 50-degree liquid. It'd just be hot water, right? It's actually really hot, like way more than lukewarm. I wouldn't drink coffee much hotter than that, but I drink pretty cold coffee. Everywhere from C to D, all that we see happening is the temperature's increasing very clearly, right? And it's in what state? Liquid water, temp increasing. So I don't like that red, it's hard for me to see. Liquid temperature is increasing. Now, water temperature, and this is all at just standard 1 atmosphere of pressure like we were doing it outside or in the lab. We can keep heating up the water until we get to this magic number where it's completely as hot as that liquid is ever going to get. At this point, delta, from D to E, we are making a change. When you heat up liquid water really, really hot, eventually it starts doing something. What was your word? Boiling. Vaporizing is another word for it, but boiling is more common. So what we see, just like the ice, there's a point where we're going to have 100-degree liquid turning into 100-degree steam. Now, if this is all kept together because the steam wants to rise away because it's less dense than regular liquid water is, we see a change of state happening. Liquid, and boiling is okay. I'm fine with using that. Liquid begins boiling. And it boils all the way from point D to point E. That's just our water no longer being liquid. At some point, all the liquid water is gone. And it's all vapor. Like, that's going to happen. If you've ever left a pot on the stove, like it does happen, then what happens? So it might float around, but if we keep it contained and we keep adding energy into it, we just make hotter and hotter and hotter steam, right? So all the way on, we just have E through, and I'm just going to put question mark instead of infinity. All that we have is, instead of ice temperature increasing or liquid temperature increasing, what is it?
Gas.
A gas or a vapor, whichever one you'd rather use, vapor temp increases. If you ever do HVAC work, and you're looking at like a heating system, a lot of the times there's water that runs through. Like here on the island, we use a lot of boilers, which literally is just water pushing through there. But at a big, like in a large building, steam is much more efficient because you can get way more energy into steam than you can liquid water because of this. Now, steam, if you just hold your hand over a pot of boiling water, doesn't hurt very bad unless you get like really, really close. Because as that steam rises, it starts to cool down immediately and it'll condense back around. If you have a super high pressure pipe with steam in it and you puncture a hole and it sprays out steam, you think that steam's going to be the same temperature as the pot of boiling water on your stove? No, it's going to be like hundreds and hundreds of degrees Celsius, scalding burns, like 3rd-degree burns from water. You can light fire with water vapor. Like, you can make steam hot enough to light a piece of paper on fire, which is weird to think about because you're literally lighting a fire with water. Okay, beyond this, water does a bunch of other weird stuff, but I think we're at a pretty natural pause point here. We will continue this after our survey. We're going to go do a survey. The weather's like perfect for it today. Cool. If you need to grab a jacket, I haven't been outside. Was it super cold at lunch today? So jacket?
Pretty cold, yeah.
Okay. Yeah, it was really cold this morning. Okay, we're going to continue this afterward. All right, so here we are. We were looking at these. All of this gets thrown into disarray here in just a few minutes as we look at it. Now, when we look at the physical world, and it feels like we're in a physics or chemistry course right now, you guys, I'm almost sure of it, have talked and heard about density. What is density? So it may be hard to explain. Could you tell me what's more dense if I give you a couple objects? Styrofoam or lead? Lead. What's different about them? So, ooh, that's the word I was looking for. The same volume of lead would weigh so much more than the same volume of styrofoam because of the compactness with it. So, we will be dealing with water, and liquids just in general. Water is a liquid. They do something very different. When we look at density, and we need to because varying things within our natural world change the density of water. And we need to make sure that we see how those work because it turns out there's a lot of ocean currents and things like that that we deal with. So I'm just going to say by first definition, I'm always going to use exactly what you said, Dwayne. We're going to say the compactness of matter in a given volume. So, and I think I just stopped there. We just say compactness of matter. Now, very specifically, when we look at this, there's two ways that this is normally measured, and by that I mean units. When we're looking at how densely something is packed or how compact it is, you need the mass, which, how do we measure mass typically?
Weight.
So mass and weight are similar ideas, but not quite the same. We treat them as if they are the same. Terrible choice, just educationally speaking, but not quite the same. If I said, hey, I have a mass of, what sort of values would I give you? Grams would be one, or pounds would be a weirder one. I would say kilograms, but pounds is definitely what you would normally use. As we look at this, two ways to go through this. We can say that it'll be grams per, and then we're going to look at something. If I write ml, do you know what this is? What is it? Say it again. Milliliter. Now, on this one specifically, and you may remember this from science, 1 milliliter is exactly 1 centimeter cubed. So a cubic centimeter is the same as a milliliter. 1 mil of water is just the amount of water that fits in a 1 centimeter by 1 centimeter by 1 centimeter cube. That's it. Oh. Tell me to turn it off here. Cool. Now, alternatively, if we're using bigger amounts of stuff, maybe a gram is too small to make sense of. So the next step up would be kilogram, but we wouldn't go per milliliter anymore. We would go per liter or cubic meter. So we'll go kilogram meter cubed. Okay, here's a weird idea. In your experience, you've dealt with temperature, whether you've looked at it like specifically or not. Typically, we know what happens with stuff. The colder something gets, how does its density change? If you were all particles instead, and I said, okay, you can't wear coats, we're just regular clothes, but we're going to go outside, you're going to be cold, right? How do people get warmer when they go outside in that situation? You might move, or you huddle up like penguins do. Like, that's what happens. Which means, in your experience, I imagine we can agree the following has typically happened. As stuff cools, as things cool, and I like to think of like specifically metal, as things cool down, they condense. Now, they squeeze together. We've seen that happen. Similarly, if you have a bolt stuck on something that just won't come off, and you want to be able to get it out of there, what do? You heat it up because it does what to it? Makes it expand. Now, on that other side, entirely up to you if you write it, I'm just going to say, as things warm, they expand. Okay. That is not a shocker, I don't think, to anybody probably. Is water a thing or a stuff? Yes. Yes. Okay. We see this happen mostly, but there's something weird that you probably never thought about that's just bizarre, and it's one of the really unique things about water. If I heat up water and it turns into a gas, is it more dense or less dense than the liquid? Is water vapor more or less dense than liquid? Less. It floats above it, right? And that's exactly what we'd expect. Okay, let's start cooling water down though. If I have 90-degree water, which is like scalding hot, because we're talking Celsius here, wouldn't touch 90-degree water, and I compared it with 30-degree water, which one do you think is more dense? 30, okay, you're right. How about 30-degree water and 10-degree water? 10 is probably more dense, right? Okay, how about 10-degree water and 5-degree water? 5 should be more dense, right? How about 5-degree water and -1-degree water? You want to say it's more dense, right? That's a natural thing. Here's the weird part about this, though. And water is weird. You guys ever seen ice? You ever seen ice in water, like ice water? Your ice always sinks to the bottom, right? Because it's more dense because it got colder? Huh. So, turns out it doesn't even matter about the air. You could freeze ice in a vacuum and the same thing happens. That's a great thought, though. Now, as we look at this, there is something really strange that happens. Water, or H2O is what we agreed we're just going to use, gets more dense as it cools, and we're going to underline this, until approximately 4 degrees Celsius. At 4 degrees Celsius, our water starts getting less dense again, which is super duper weird, because in every situation that you've probably ever paid attention to, we know hot air rises. That's why we have fans, or whether you're pulling the air up or down. Last year we encountered this hands-on in the hatchery, because we were taking the water temperatures, and what we saw was the top was 4 degrees, but down below it was 5 or 6 or 7. It was like varied like that, and it was like, why on earth would this be the case? Because this is a weird property of water. Now, even more than that, ice, if it were to follow this, you would think that ice would just sink. It doesn't. Ice expands, and it instead forms this nice crystal structure as it turns into ice instead of liquid, and that crystal structure produces the space. It's not the air in there. It's that structure that it forms. It's a weird thing that happens. Okay, why is this so important to life on our planet? Why does it matter to you as possible fisheries scientists or marine scientists that water stops getting more dense? What if it didn't? What would the ramifications be? Yeah, say it. What you just did was the motion I was expecting, unless that was completely unrelated to the question. You guys ever seen a lake? Like there's one right there, yeah? And lakes freeze, yeah? If ice didn't do this, or if water didn't do this, when ice formed, it would literally just sink down and crush everything underneath. And life would never have a chance to prosper on this planet. Like, it just wouldn't happen. Okay, as we get going next class, and tomorrow, on the agenda so far, we have a couple different things. First one that we'll do is we're going to go ahead and check out that footage. And by we, I mean you guys. I will have to upload it to the Google Classroom because your computers can't get on YouTube, right? Okay, tomorrow, make sure that one person in your group has a laptop because we're going to be watching the video. Cool. All right, no additional homework.